Welcome everybody to our part 2 of our Canadian Ag Forest Meteorology session on understanding past, present, and future effects of climate on agriculture and forestry and water resources. And to get us started today, I'll welcome Jacob Mardian, who's a student at the University of Guelph, who's going to be talking about interpreting drought on the Canadian prairies using machine learning. So Jacob, if you want to go ahead, you can share your presentation.
Okay. Okay, thanks, Catherine. So my name is Jacob Mardian. I'm a student at the University of Guelph and a research affiliate at Agriculture and Agri-Food Canada. And today I'm going to be describing a framework we developed for monitoring and interpreting drought on the prairies. And I'll show you some of the early results we've got so far. The other authors of this work are Aaron Berg, Barry Bonzel, and Catherine Champagne. So drought is a costly natural disaster. This chart is showing the agricultural losses due to drought from 1983 to 2009. And as you can see, Canada is amongst the top countries in the world with estimated losses of about $6 or $7 billion. I'd like to point out that the majority of these losses are from wheat production in the prairies. And the prairies are particularly vulnerable to drought, being the breadbasket of Canada and frequently experiencing drought. So there's a need for drought monitoring to understand these impacts across the country. Our national framework to do this is called the Canada Drought Monitor, and this is produced monthly by Agriculture and Agri-Food Canada. And you can see the location of drought as well as its intensity on a scale of no drought, or the base map here, through D0 or abnormally dry conditions in yellow, and then we have 4 categories of drought, D1 through D4 shown in brown to red here. Now this drought monitor is produced through an interpretation of multiple data sources. This includes a machine learning model and includes sort of expert inspection of this data to fix clear errors in the model. There's some consultation with local experts who may understand drought impacts on the ground, for example, those in water resource management. And then they use their expert judgment to produce these maps based on different sources of evidence. Now, this is quite a robust approach. This is used in the United States and Mexico as well. However, this human component, this reliance on expertise, can make it difficult to understand the drought monitor, or, for example, why a certain category may have been assigned. So that brings me to our objective, which is kind of twofold. So the first, we wanted to build a machine learning model to replicate the drought monitor. So can we do this in an objective and data-driven way? And the second part of this is, can we interpret that model to gain some insight into the drivers of drought? And that second part is really what I'll be focusing on today. So our study area is the prairies, right? Encompasses much of Alberta, Saskatchewan, and southern Manitoba. It's about 50% agriculture, shown in yellow here, with the other 50% being split between wetlands, forests, grasslands, and urban areas. So this really makes it a good candidate to test our model, right, to evaluate some of those costly impacts on agriculture, but also generalize our model to more diverse landscapes. So I won't get into the machine learning portion too much, but we do use an XGBoost machine learning model to predict drought monitor categories in the prairies. Oh, I think I got muted there. Can you hear me?
Yes, no.
Okay. So we developed a machine learning model from 2010 to 2019 to monitor drought, and we do this using 50 or so climate and satellite indicators. These are related to precipitation, temperature, soil moisture, vegetation, and so on. So machine learning are typically called black box models, right? We can see the data that goes in, we can see the predictions that come out on the other side, but we really don't understand what's happening internally. It's a black box. And this can be problematic if we're trying to study and understand drought or some other phenomenon. So we use SHAP values, which is a technique to sort of reverse engineer any machine learning model and open up that black box and see what's inside and really understand why predictions are made. So this technique does this by quantifying variable importance for each observation. So think, a single pixel in June 2022, we have a drought prediction, let's call it f of x, and we can reformulate that prediction as a linear model. So, basically if you know y equals mx plus b, this will make sense. We have beta naught, which is our y-intercept, plus the effect of all of our different predictors. And so if we can understand the effect of those predictors, we can get some insight into those drivers of growth. Okay, so to give you a visual representation of what I'm talking about here, I've selected a random D3 pixel or an extreme drought pixel, and this is the model output, okay? So we have a base value of 0.02. Basically, D3 drought occurs 2% of the time. So if our model didn't have any other information, if we didn't have any other predictors, its best guess would be that there's a 2% chance of drought occurring. All right, so that's our y-intercept. However, our model actually predicts a 48% chance of D3 drought in this case. So normally we ask the question of, well, why is there a gap there? Why did our model make that prediction? And so you can see our SHAP values here. All of our predictors in orange are increasing the probability of a D3 drought, while all of our predictors in red are actually decreasing the probability of a D3 drought. And these will all add up to 48%, of course. And so how you can begin to interpret this, I'll give you a very basic example. We see the Palmer Drought Index and SPEI 12. These are basically measurements of relative dryness or wetness. And with values of about -2 or -3, indicates the area was much drier than normal at this time, which of course increased the probability of a D3 drought occurring. So this is the basics of how this framework works. I'd like to remind you this was just the output from one pixel. We have 84,000 pixels in the prairies over 12 years. So we have about 10 million of these. And as you can imagine, we can begin to analyze these values in all sorts of interesting ways to gain insight into drought. So for example, we've looked at the relationship between teleconnections and drought, or some of these large-scale climate patterns. We look at the top row here, we have our multivariate El Nino index. And it didn't appear to have any strong relationship to the no drought or abnormally dry categories. But where it gets really interesting is we see that negative MEI values or La Nina conditions were strongly related to D1 or moderate drought conditions, while some of our more extreme drought categories, are D2 through D4, were related to positive MEI values or El Nino conditions. So this is interesting to see that kind of both extremes in the El Nino Southern Oscillation are related to drought, but perhaps have different intensities or manifest themselves in different ways. And we've done this for the Pacific Decadal Oscillation as well. And there's a strong relationship there, as well as the Pacific North America pattern. And so we can even map these SHAP values, or these variable importance, across space. So you're looking at the spatial variability of the El Nino Southern Oscillation's importance. And these areas in yellow here have a very strong teleconnection between drought and these processes happening in the tropical Pacific, whereas these areas in blue have little to no relationship to the El Nino Southern Oscillation. We can then aggregate these values across our entire study area and our 10-year study period and look at what are the most important variables for predicting drought in general. And we find that our top variable there is PDI, or our Palmer Drought Index. Again, this is a measure of relative wetness or dryness. And we can even see its importance on predicting each drought category. So for example, you can see it with the larger gray bar there, it's quite important for predicting no drought, but not as important for predicting D2 through D4, some of these more extreme drought values shown in these red and purple colors. Really, to understand the more severe droughts, we need some of these other data sets shown. So I've even grouped together some of these values to try and understand what types of data sets are optimal for drought monitoring. At your 12 o'clock, we basically have our climate data, which is of course important for predicting all categories. At our 6 o'clock, we have teleconnections, which again, quite important across the board. If we look at our 3 o'clock, we have our GRACE satellite, which is quite interesting. It's a satellite that can measure total water storage. And actually, we're estimating groundwater levels. And it's quite important in predicting drought, but especially those more severe droughts, right? The D2 through D4, which really tells us that the most severe forms of drought on the prairies are characterized by groundwater shortages, and these can be detected from space. So in conclusion, this research provides a framework for operational drought monitoring and interpretation, so we can use it to provide timely updates to drought status, but also study and learn from drought events as we go, and hopefully incorporate that information into our models in the future. We also found some preliminary results that drought exhibits a strong relationship to the El Nino Southern Oscillation, the Pacific Decadal Oscillation, and the Pacific North America pattern. And finally, the most severe droughts are associated with low groundwater, and this can be detected using the GRACE satellite constellation. I'd just like to quickly acknowledge some of the funding, and I'd be happy to take any questions at this time.
Great, thanks, Jacob. So if you have a question, you can type it into the chat, or we only have a couple minutes, so if you want to,
I have a quick one.
Yeah, go ahead.
Yeah, Jacob, very good presentation. I just noticed in your last slide that soil moisture did not, I guess, yeah, in that diagram, is not really a huge contributor to the explanations. And the quick question is why? It puzzles me.
Yeah, no, it's a very good question. I noticed it was quite highly correlated to the Palmer Drought Index. So the model may have been, taking the Palmer Drought Index instead. The soil moisture data set we use is the ESA CCI, the Climate Change Initiative, which blends various soil moisture data sources into continuous data sets. So it uses CMOS and SMAP, for example, at different time periods. So it could be that some of the calibration between these different data sets wasn't optimal, and it wasn't really capturing these anomalies effectively. But really, I'm not 100% sure.
Great, thanks. Anybody else have a question?
I have a quick one. So when you try like this, correlate the, there is a forecast, like have a lead time, or just use all the data?
So this is a monitoring framework, so we only use historical data at any given time, just like the Drought Monitor does.
Okay.
Yeah.
Great, thanks, Jacob. Okay, we'll move on to our next presenter. So our next presenter is Richard Agyeman. He's going to be talking about projected changes in hotspots of agriculturally relevant compound events in Western Canada cropping regions under the RCP 8.5 climate change scenario. So go ahead, Richard.
Hello. Yeah, so thank you. Yeah, my name is Richard again. Today I'm presenting on the projected changes in the hotspots of agriculturally relevant compound events in Western Canada and RCP 8.5. Sorry, yeah. So the Western Canada is prone to drought, heat stress, and other extreme climate hazards that impact agriculture. When multiple of these extreme climate hazards occur together, 10 compound events can exacerbate the impact of climate on crops. With the projected changes in climate, that's warming expected in climate in future, it is anticipated that these compound events will multiply in Western Canada, and the goal of this work is to assess these changes because not much work has been done in this area. Also, high resolution climate models are able to better simulate how climate change will alter extreme events in future, especially extreme precipitation events, which are strongly affected by convection. East of the Rocky Mountains hosts most of the croplands in Western Canada. These areas are semi-arid. Mean precipitation annually is below 600 millimeters. This work is actually going to focus more on cool season crops that are traditionally grown from April to August. Two different climate simulation data is used for this study. That's a weather research and forecasting model at 4 kilometer resolution forced by error interim reanalysis data. And for the future simulation, the pseudo global warming approach is used here, using this ensemble mean difference between 1975 climate models as a global warming increment on error interim reanalysis data to force this data, to force WRF for the future simulation. For more details about this data and model evaluation, see Lee et al. 2019. At 4 kilometers, the model is able to explicitly resolve convection and adequately resolve topography, which makes these higher resolution models able to simulate some of these physical processes that affect precipitation better than cost resolution climate models. So the 15-year data for current climate and future climate are bias corrected using the multivariate contour mapping method. For model evaluation in this study, the annual spring data was used. So for the different climate hazards considered in this study, we have drought represented by SPI values below 0.5. And for extreme low precipitation, the 10th percentile precipitation is used. For heat waves and extreme heat, because we are considering co-season crops, the threshold is 30 degrees C for heat waves and 35 degrees C for extreme heat. For cold waves, we have minimum temperatures below 5 degrees C. In this study, the return period is used to represent the hotspots of these compound events in Western Canada. The likelihood multiplication factor, LMF, is used to assess the relationship between these hazard pairs in forming these compound events. Where the LMF values are able to reproduce the hotspots shows that this, the drivers forming these compound events are likely to be from same driving mechanism. And when the LMF values are high, shows that gives an indication of how severe these compound events could be. The results. So I have results for heat waves and drought in my first column. Second column, I have heat waves and low precipitation. The upper panel shows observed data, that's the result from annual data. For control simulation, that's the model simulating present climate at the middle panel, then for future projection at the bottom panel. As we can see, the model was able to some extent reproduce the hotspots of these compound events in current climate, except for the extreme north of Western Canada, north of 60 degrees latitude, where some overestimation is recorded, which could be due to data issues in annual spring or the model just overestimating. For heat waves and, okay, so this panel shows extreme heat and drought. Then I have extreme heat and low precipitation. Again, the model was to some extent able to reproduce the hot spots, though underestimating it over the prairies. And in future, the model is showing that these compounded events are going to expand geographically to affect most of the prairies and the Okanagan Valley that also produce some cold season crops in Western Canada. We also consider the combination of cold waves occurring during low moisture periods like drought. So we have cold waves and drought, then cold waves and low precipitation. And the results are showing that in future, most of the prairie areas may not see some of these compounded events, except for the extreme eastern part of the prairies, eastern part of Saskatchewan and the western part of Manitoba. The LMF values here showing, so I have the combination of heat wave related compound events in these two panels. So we have heat waves and drought, heat wave and low precipitation combined with a dose from extreme heat. The results are showing that over the prairies, the correlation is positive, though not so highly positive for both current climate and future climate. For low precipitation, we can see low precipitation occurring together with heat waves. We can see that a mixture of both positive areas and negative areas for these compounded events. If you look at the extreme heat and drought, you can see that the LMF values are positive and high, both for current and future climate. And this gives an indication that these compounded events will be driven by same driving mechanism over the prairie region. And some of these drivers for heat wave and drought include upper level circulation anomalies, also atmospheric oceanic teleconnections in this region are also responsible for some of these compounded events. Another driver over this region is the quasi-stationary mid-tropospheric ridge, which actually displaces jet streams and cyclones that are responsible for precipitation northwards, so that this driver creates favorable atmosphere for adiabatic warming, which leads to low precipitation and heating a high heat over this region. For the LMF for cold wave and drought, cold wave and low precipitation, as we can see, because most of this region may not see this much of these compounded events in future. Some areas are looking negatively correlated, but few regions still shows some of the positively correlated region, and some of the drivers that are responsible for cold air influx or advection of cold air into this region during dry years include the anomalies in geopotential height gradient between the Hudson Bay and the Prairie provinces. So in summary, the projections are showing that in future, these compounded events will actually expand to cover most of the croplands in Western Canada, and significantly could extend all the way to the Northwest Territories, and that some of these compounded events, especially drought and heat, extreme heat, will result from similar driving mechanism, which could make this compounded event more severe in future. That's all I have for you today. Thank you, and we'll be waiting for questions.
Great, thanks a lot. Okay, we have a question from Paul. Should high SPI values be considered as a potential stress factor for compound extreme events?
Because in this study, we are considering agricultural drought. That's why the SPI value I use is a bit low, 0.5. And I actually pick up this value from some previous studies that actually use 0.5 as the threshold for agricultural drought. I actually did an analysis for -1. Using -1, the results are not much different, though, yeah, a bit more, especially in -0.5 compared to -1. Yeah.
Did you, I might have missed this, but did you look at evapotranspiration impacts? So if precipitation, sort of those compounding the high temperatures and the high precipitation values, to see if there's a sort of a higher water loss associated with any of these events?
Please, the question again.
Oh, did you look at evapotranspiration in any of your models?
No, I didn't consider evapotranspiration in this study. So, yeah, maybe if I were using, say, SPI as an index, that would surely use evapotranspiration. But I use SPI, a simpler model, yeah.
Great, thanks. Does anybody else have a question? We have 1 minute.
I have a quick one, Catherine. Richard, good work. Based on what we heard this morning from the work of Paul Bullock, we can have these events within the same year. You begin with very wet conditions, then it becomes very dry, and or vice versa. I'm wondering, do you have the compound events that you have presented? Do they have a timing associated with them, or are you just analyzing for the entire season? Or is it something that you can really drill in a little bit and say this is what we expect during the first part of the growing season? This is what we expect. I'm more or less driving at doing a seasonal analysis. Is that something that would be done with the results that you have?
Yeah, I think it's a very good question, and I can look at it to see how, yeah, so to look at maybe say the first part of the season, the middle part of the season, maybe, yeah, and the middle part of the season, what comes to mind is to split the data, maybe just pick first part of the season for each year within the time frame and use it and compare with picking the second part of the season, or say a portion of the middle part of the season, and compare the results. That's if that will work, I think that would be great. Yeah. So what I actually did was to just consider the entire season for each year. And I think I will have to think about your suggestion and see. I think it should be very useful if you can do something like that.
Great, thanks, Richard. Okay, we're going to move on to our next speaker. Vanessa Ford is going to talk about integrating climate change research into forest and natural resources management in northern BC. So Vanessa, go ahead.
Okay, just checking that you can see my presentation.
Looks good.
Perfect, thank you. Happy to speak to you guys today. I'm going a bit off on a limb here, but I'm going to try to focus on some successes and failures I've had at trying to integrate climate change into forest and natural resource management in northern BC, rather than talk about methods, results, and findings of a specific project. I'm mid-career, and I thought that given the theme of the Congress of Science Serving Society, I was hopeful that that kind of lesson learned would be useful to a group like this. So we'll see how it goes. So the bulk of the problems that I deal with as a research climatologist for the British Columbia Ministry of Forests is that we're seeing increasing forest disturbances across the province. We saw 18 million hectares impacted by the mountain pine beetle, which resulted in a huge loss of timber, as well as the record-breaking wildfire years of 2017, 2018, and 2021, with over 3.4 million hectares burned. And to a lesser extent, we're experiencing increasing forest pathogens, which are also leading to mortality, a growing spruce beetle epidemic, increasing losses due to drought, including, unfortunately, the loss of millions of seedlings as a result of last summer's heat dome in British Columbia, and also a rise in defoliators, so pests that actually mine out the chlorophyll of certain tree species, and decrease photosynthetic capability. All of these things are also impacting the ability of our forests to mitigate climate change impacts. So at the same time, we also have increasing climate change. Lucky enough, in the area that I work in northern British Columbia, we have a nice long weather station record going back to 1895 in Fort St. James. Thank you, Environment Canada. That is telling us that we've seen greater than a 3-degree temperature increase over that nice long record for this part of the province. And looking at projections down below, we see that regardless of scenarios, of course, temperatures will continue to rise. Most of the warming that we're experiencing in northern British Columbia has actually been in the winter months, but the projections are telling us that our summer months are going to be experiencing just as much warming in the future, which will lead to even more forest disturbances. So how do we relate climate change and forest disturbance? So we need a lot of data and research. I'm lucky enough to work in a pretty good government research program. We just celebrated 100 years of forestry research in British Columbia last year, which is pretty cool. So we have a lot of data and research to understand these things. But then once we do think we understand these things, how do we make that information useful for foresters and forest managers? The short answer, although I'll get in more details, is we need issue-specific tools that integrate with climate models. And then once we have that, how do we reduce the impacts of climate change through changes in forest management? Well, that, of course, is a lot more challenging. So I'm going to give an example of how some of us are trying to integrate climate change into forest and natural resource management by telling you about a forest drought risk assessment tool that we've developed. I won't get into too much detail of the tool, but more just talk about the process using the tool as an example. So we started developing this tool back in 2010 as part of some climate change science and forestry funding. It was advised at that time that climate change projects needs to be developed with multidisciplinary research teams, which we did, and that we had client consultation and engagement during our study design, which we also did. Just a brief overview of the input into the tool for those that might be curious is basically it takes historical weather station data. It accesses information from our ecological classification system in British Columbia, which tells us where we have tree species on which sites or not on which sites. It also integrates soil characteristics, the most prevalent one being soil moisture regime. And then we integrate climate models and also a water balance model to get at that drought component. The water balance model we use is basically actual versus potential evapotranspiration. And then the output is current and future risk of mortality of common BC tree species. And so the first step of this work was to really make sure that the information would be accessible to forest managers and decision makers. So of course, as scientists, we all publish. We've published internally in this case, because this is really an internally focused tool. So showing some examples on this slide. And then we also wanted to make that tool accessible online for folks to use. So basically what a forest practitioner could do is once they know what ecological unit they'll be working in, they can go and use that Excel tool and input their site and information about their soil moisture regime and get an output of tree species specific mortality risks in the future. And then we also wanted to develop some web tools to make the uptake of the information even more digestible, and showing an example of that there. So people could spatially see what areas might be of current and future risk of drought. And then the next step is really to communicate. I didn't really realize at the time how important this step is. So we've put a lot of effort into communicating our results. In the plenary yesterday, for those of you who attended, there were some good tips on how the use of really good visuals are important for communicating science results to decision makers. So we've tried to make what we hope are some good visuals of the output of this drought tool, as opposed to a clunky Excel tool you saw on the previous slide. So I'll just briefly go over some of the model results. So for example, we're able to display tree species specific risks by geographic area. This is the central part of the province of BC. And what I'm showing on the left is the current risk of drought in spruce leading stands based on a baseline climate of 1961 to 1990. And then the bottom graph is the future risk of 2050s. So you can see that areas that were potentially under moderate stress have now moved in part to high risk of mortality from drought stress. And then when we look into the 2080s, there's a lot more area of potential mortality in these spruce leading stands for drought risk. So looking at the figure on the top right, managers and decision makers could use information such like this to say, okay, in those areas of high drought risk, how do I want to manage that forest? Do we potentially harvest early? As we know that moisture stressed stands can also be exacerbated by other natural disturbances, such as they're more likely to see pests, pest populations explode and lead to pest outbreaks. And also it can be potentially a wildfire risk in terms of drier fuels in the area. And then also a forest manager could say, okay, those green areas where we have low drought risk might be areas that we want to protect or keep for the future in terms of timber supply. So communication being important, we've done numerous presentations, of course, at science conferences, but also making sure to hit internal clients like forestry meetings, internal working group, regional districts, engaging with wildfire experts and other decision makers. Yeah, we've learned through this process that few people outside of scientists and researchers read scientific publications. So making short little summaries of your research findings in relevant newsletters, research summaries, and also making good visuals and mapping products as the information has been really valuable. And then the last step is really application. So as mentioned, we started developing this tool in 2010, and the bulk of the work was really done by 2012. And then the uptake was amazingly slow. And this is an example of other projects that are looking to understand the impacts of climate change to inform management decisions. It's not just this project where the uptake has been slow. And so while we were waiting for that uptake to occur, we really focused on making sure we developed publications that talked about the application. We also in the background worked on our field validation to make sure that our tool was representing things appropriately and making adjustments as necessary. We looked at other methods that might be easier for folks to understand, like using drone detection for drought stress. We also took that Excel tool and put it in an R Shiny app, which hopefully we'll be able to publish online later this year. And then also taking that information from our tool and making sure we translated it into impact. So in this case, at the bottom left there, I'm showing an example how we used the results of the drought risk and translated that into the impacts of timber supply, showing that for this particular area, there can be very large impacts to timber supply. And then once that work is done, we can do sensitivity predictions on different ways to manage those risky forests. So some of the lessons that I've learned through processes such as this one, as mentioned, unfortunately, few will read your papers except for other scientists and research. So those short communication notes are really important. We did a recent survey of our provincial research program last year, and it showed that only 13% of our clients accessed our papers. Most of the information they got directly from contacting us or from presentations that we give. Also, few will get it. So this requires additional education and training, making accessible tools and having good visuals. And you may need to give the same presentation many times over before people get it. Unfortunately, few people care until the impact is fully realized. So as mentioned, when the bulk of this work was done about 10 years ago, we hadn't seen the impacts of drought mortality to our forests that we're seeing today. So our best efforts at this early warning were largely ignored, which was unfortunate. And this, of course, is a challenge for all of us trying to avoid future impacts of climate change. Governments are focused on current issues, and this is a big challenge for us. And that change takes time. For us, it was about 10 years before foresters and decision makers started using this information to make management changes. And climate change, of course, doesn't wait for your research to be perfect or for decision makers to get it. And my advice is while you're waiting, just keep working on it. And then some other recommendations is to work with intended clients during your study design. This includes the need to include relevant decision makers so that they're on board at the start of your project to increase the uptake of the information. I mentioned frequent communication. And this is more about communicating the concepts. So I had to spend a lot of time early in my career educating people on climate change before I even could get them to think about climate change and drought impacts or wildfire impacts or landslide impacts, whatever we were talking about. So making sure that the concepts are cleared, concepts are clear and your details in your research publications are the supporting information. That detail is still important. We can't just give managers climate model projections of doom and gloom. They need to integrate with a particular impact like we did with tree mortality risk in that example. Making it operational has been a good lesson that we learned. So as mentioned, we made our drought information available by the same ecosystem units that forest practitioners use to make their decisions. So then it was just an easy adaptation to what they were already doing. And then making it relevant in terms of quantifying the impact of potential resource losses and equating that to social economic losses like the loss of a viable forest industry. And then offer solutions. This tip has just come up in the last 6 months or so. Decision makers are really asking for us to include operational or policy implications with our research work, as well as potential mitigation options. And these should really be developed in collaborations with other experts. Short, snappy messaging is also really effective for communicating to decision makers. So this is like a digital version of your elevator pitch. So you can easily send this to decision makers, hopefully for increasing the uptake of your results. And that's it. Thank you.
Great, thanks a lot, Vanessa. Okay, we have time for some questions. So Yinso asks, are these online apps available to the general public?
Yes, they are. As mentioned, our Shiny app isn't up and running quite yet, but we hope it will be soon. It has to go through our communication folks first.
Okay. And question from Etienne. Thank you for the presentation. I see you recommend including relevant decision makers at the beginning of your study design. To what extent and how would you say you were able to do this in the context of this project? Did you have a good idea of who the potential users of your tools would be? Did you have a few keeners willing to speak to you? And did you have extensive continuous conversations with them as you were developing the tools?
Yeah, for this particular example, I mentioned that we involved our clients early on. And then one of the lessons learned is we really should have also involved the decision makers. So in my example, the client was timber supply analysts in order to bring climate change into timber supply modeling. But as mentioned, we learned that having decision makers involved in early would really allow them to be able to understand as well as get their ideas on how to best present the information for them because they are the ones making the decisions on how that timber supply is going to be used. So no, we didn't include them. And I've learned that in my current projects, we're including them.
Great. I have a question. This is something we run into in agriculture, that especially with your future projections risk maps, in terms of both the spatial resolution of the climate change projections, but also the sort of temporal resolutions. Sometimes these 30-year projections seem too distant for resource managers to use. I'm wondering if you ran into that and if you did it, or what you did to kind of make that information more relevant.
Yeah, so I certainly wasn't showing all the outputs available for this particular product. I think it's easier in forestry to have folks look at longer term projections, but I totally get how that wouldn't be really as beneficial for the agriculture industry. So there's lots of data available for shorter term projections now. So one of the things we did, we also modeled, the current period we're in, which is technically, a modeled forecast, and then compared it to the current data. And we were able to show that in terms of drought risk, we were already in that projection as opposed, sorry, we had gone beyond that projection based on current conditions. So that was kind of an interesting learning, looking at those shorter term prediction periods. But there are shorter term information products coming out every day that I think would probably be more applicable to the agriculture industry.
Great, thanks. Does anybody else have any questions? If not, I think we have a 5-minute stretch break built into our session. So thanks, Vanessa. And we're going to start our next talk in 5 minutes. So if you want to take a stretch break or grab something to drink, and we'll start back again in 5 minutes.
Ray, please, were you able to resolve your PPT?
I'm Richard. He sent it to me, so I'm gonna share my screen, and Ray will let me know when to advance the slides.
Okay, thank you, Prof. Yeah.
I'm just thinking, Timmy, maybe it's better to do it sooner rather than later.
Okay, yeah, I can share my screen.
I don't use Zoom very much. It's quite a challenge getting this far.
Yeah, hopefully we can return to in-person meetings soon. Okay, let's see.
I don't think I have to do anything, eh?
Now you would just let me know when to advance my screen. So I'm gonna share my screen. You should see it shortly. Yep. No, I think you're saying the wrong thing. I'm gonna stop that. Sorry.
That's the first slide.
Yeah, I need to do that again.
Yeah, that's the first slide.
Yep, that's good. I'm just gonna move this away. And that's advancing, right?
Yeah.
Okay, so yeah, you just let me know when to advance the slide.
It's a little hard to read parts of this thing.
You can make it bigger on your screen, I believe.
Okay, how do I do that now?
Or the other option is if you have a copy opened on your computer, you can just present as if you're on your computer, but just let me know when you are.
Yeah. No, I can see I'm enlarging it now, so.
Okay, good.
Okay, we'll get started. Richard is back as well. We can start the recording. Okay, we'll get started with our next presentation. So our first talk of the second half of the session is from Ray Garnett, who's going to be talking about the severe drought of 2021 over the prairies. La Nina provides the forcing mechanism. So over to you, Ray.
Hello there, everybody. This was something that Matt Kanagar and I prepared. And so this is, I feel good about what we were able to do last year in terms of anticipating that drought. And I'm just going to show you the various details that I have on what actually happened with that drought last year in 2021. And so we might as well get going there, Timmy. Next. This map here shows various agricultural ecological zones over the prairies. And what happened last year that was really exceptional was the dry July. A mere 36% of normal rainfall in July, 62% of normal in June, and May was fairly reasonable. But look at the temperatures here. We had 2.9 degrees Celsius in June, 2 degrees Celsius in July. And those June, July, based on my data, was the driest since 1967, 54 years ago, June, July. And so it was an extreme drought and something like we haven't seen in over 50 years in terms of dryness. Next. So this is a listing of the stages of a spring wheat crop. There's tillering, stem extension, there's heading, and then there's ripening. And in my experience, sorry, I've got a phone that keeps wanting to ring here. And rainfall, I found that July rainfall at heading is probably the single most critical growing season factor. And the two most critical months, that actually happens in July and June, of course. So you can think in terms of May during tillering, stem extension happens during June, and July is the time of heading. And of course, August is ripening. So if you tried it in a normal kind of a growing season. So the biggest factor in terms of the growing season is July precipitation. Then we have June and July is probably the second most important, June and July precipitation during stem extension and heading. And then low temperatures in May can adversely affect germination and tillering. So those are the basic weather factors during the growing season, and when they occur, they can affect yield. Next slide. So this, and spring wheat yield and rapeseed yield for that matter, is a proxy for climate. And you can see that 2021 was extreme. It was a 20% crop off the trend yields. And you could probably compare it to 2002 and back in 1988. Those are also very extreme droughts. This is kind of a detrending of that yield series, a linear detrend, and you can see just how it compares if you take out weather. So this slope here has to do with fertilizer, new varieties and such. So yields are going up, but there are considerable variations, as you can see. And so that kind of tells the story. Good yield series has lots to say about the climate. Next slide. This is a conceptual diagram of the paper we did in 2006. And what we published this in 2006, and we look at the various factors that are behind a wet summer and a dry summer. In a dry summer, typically it's high solar activity, you get an easterly phase of the QBO, and La Nina is typically what happens, but is behind a dry summer. So there's different, we looked at 4 different forcing functions in this, one being sun, one being a stratosphere, one being the El Nino Southern Oscillation, and the other being the snow. And So in 2021, La Nina definitely overpowered the whole situation, overpowered actually low solar activity, a westerly phase of the QBO, and below normal snow. So it was exceptional in that it overpowered the other three. And usually they work in unison to some degree, but not in 2021. Next slide. This is the slide that is very useful. I look at, in fact, I maintain that this is a fact that the Asian monsoon and El Nino Southern Oscillation occupy the single largest source of interannual climate variability globally. And as Bjerknes way back in the 60s has said, monitoring sea surface temperatures in the tropical East Pacific is indispensable for long-range forecasting in North and South America. Now we've had La Nina for 2 years. And what's happening this year, there's been a shortfall in production in Argentina with their soybeans. There's also problems in the US. This is the La Nina phase, what you can expect on a global scale. They're having trouble in the US. We've had 2 years of La Nina, and La Nina is unfriendly to the Americas, and well, El Nino is the friend. And so we're seeing trouble in the Americas this year, right from Argentina right up to the Canadian prairies. And I think it'll be very interesting June, July to see what happens in 2022. And okay, I think we're ready, but you can see the impacts. El Nino typically hurts the Indian monsoon, hurts Australia's situation. La Nina is just the reverse, it's a flip. So we can sort of expect these, and with the La Nina, these countries are likely to be on the wet side. And we are indeed still into a La Nina. It's likely expected to continue through the summer of 2022. Next slide. So we looked at the El Nino La Nina years. And of course, above this line are the El Nino years and below are the La Nina. It's a little hard to read, but if you do, I did a quick classification year by year. And generally speaking, in El Nino years, the rainfall in June and July is about 110% of normal. Some exceptional years are 63, 91, 2005, 2010. And La Nina years, you tend to be low, about 92%. Depends on how well you classified. I did it rather quickly, but those are La Nina years. And of course, we did poorly in these years in terms of rainfall in June and July. This is a Pacific Decadal Oscillation. You can see since about 2015 that it's been negative. And this tends to favor kind of a wetter and cooler Canadian prairie climate. And I think that's all I have to say here. But so June and July rainfalls are affected by El Nino and La Nina. And when we get the extreme El Nino and La Ninas, we can expect most of the time a fairly sizable impact on, say, June and July rainfall. Next slide. What this is about is basically sort of supporting the idea that when June, Julys are dry, they tend to be hot. This is a correlation that I found going back to about 1960, I think it was 60 years, and the R value is about minus 3.5. And dry Julys are usually hot Julys. And last year was exceedingly dry over the prairies. And you can see this is the temperature, and this is the dryness. And so there's an inverse correlation in terms of when they're dry, they tend to be hot. And it's especially in the case of Julys. And that's, as I said before, that's probably the single most important month. And okay, I think I've made my point on that one. Next. So there's other factors that occurred last year as well. And what we're looking at here is kind of how the P&A behaved starting in September. And you can see it's positive in June, July, and August. And what that means is you've got meridional north-south flow, which is conducive to dryness, a general rule, spring, summer. And that's the way the P&A behaved. So in a sense, it was conducive to dryness, and if not heat. Another one is the Arctic Oscillation. I tracked that one running right from September, and you can see it was positive in that June-July period. positive, in other words, it means a lack of cold fronts, essentially. A positive AO, a negative AO, you're more inclined to get AO, cold fronts. And these are just correlations, operational research, if you like, with various correlations that I've found over the past. And the PNA was conducive to heat in June and July, and the Arctic Oscillation, of course, was also conducive to heat. So I simply applied what happened in the real world to correlations that we discovered in the past. And so these two factors, I would say three. There was the surface to atmospheric effect of dryness contributing to heat, and these two drivers looked as if they also were conducive to June-July heat over the Canadian prairies last year. Next. Now, this is actually what was used to foreshadow that extremely dry June and July. This is a composite. We did this in 2006. These are your wet years. These are your intermediate June, Julys as far as precipitation is concerned over the years. And that's for the period 1940 to 2004 that this is based on. These are the driest years right in through here. And they were identified as 61, 67, 74, 85, and 2003. So what we did is simply operational research with this composite. We overlaid what was happening, starting in December, running through April. And you can see in April that it was pointing to a very dry June and July. And so what it does is this line in here, especially if you accumulate it, represents the sustained forcing of Nino 3 sea surface temperatures. This is in the Pacific, near the central part of the Pacific during that dry period. So that we see that as a principal driver of the dryness that happened last year. And La Nina is persisting. We've had it for 2 years now. It looks like it's going to persist into the summer of 22. So if I do it for 22, it looks very much like last year. In other words, reduced June, July rainfall. And so I say that we are drought prone once again in 2022 because we're essentially in a drought cycle, as far as I can see, 2021, 2022. As long as La Nina is on the go, we are drought prone on the Canadian prairies. Next slide. This is something we did. It's a parametric qualitative model for the eastern prairies. And you can see also that July is a meager precipitation. This is based on about 32 stations. It was very, very dry in the eastern prairies last year and very hot. And July, as I said earlier, is probably the single most important month for yields. Spring wheat canola. The Arctic Oscillation was, there were no cold fronts. This was positive. And so anyway, so these are just other predictors we looked at. These are the correlations. And these are Nina 3-4 sea surface temperatures. And they were all below normal last year. So the impact was that of dryness. So these are other factors that contribute to dryness. So there's a number of predictors, just performing in a sense operational research with a parametric qualitative model that was signaling a very dry July over the eastern prairies in 2021. Okay, so that's about it. Next slide. That's about it. The 2021 June-July was the driest in over 50 years last year in 2021. The impact on spring wheat yield was comparable to the droughts of 2002 and 1988. The sustained forcing, it was really the sustained forcing of Nino 3 sea surface temperatures, December to April, that were the main causal factors, we understand it. And when June, Julys are dry, they tend to be hot. And there's a couple of other predictors that seem to support the June, July heat as well. So that's what we came up with. And this is empirical statistical work, and it's worked. And what else can I say? We're at a time now, there's a food shortage. Grain prices are extremely high. So I like to think that this empirical statistic approach is of high value. I'd like to know if there's any global circulation models out there that what they said about the summer last year over the Canadian prairies. I'd like to know. And that's all I have to say. Thank you for your attention.
Thanks, Ray. We're at time. There is a question for you in the chat if you want to try and answer it directly, but I think in the interest of time, we'll move on to the next speaker. So our next, we're going to move east now. Our next speaker is Narayan Shrestha. She's going to talk about, so he's going to talk about land hydroclimatology of Laurentian Great Lakes region in a changing climate. Go ahead. I think you're not sharing your PowerPoint anymore.
Oh yeah, can you hear me now?
We don't see your presentation.
Hello?
I just see the video of me. There we go.
Yeah, can you hear me?
There's a bit of an echo, but yeah, and your presentation is not in presentation mode. There you go. Oh no, your presentation was good.
Can you hear me first? No?
Yeah, I can hear you.
Oh, I don't know what.
You're just not sharing your screen anymore. Or you're sharing the video screen, not the PowerPoint.
I'm going to close and then hello, can you hear me now?
Yep.
Okay, so I just restarted the entire thing. So yeah, I'm going to share my screen.
You just put it in presentation mode. Oh. There you go.
I think he muted himself.
Oh, now you're muted.
It seems that, can you hear me now?
Yeah.
Yes.
Yeah, I'm joined from the browser. As soon as I share my screen, it just mutes, I don't know, automatically. So I don't know, I don't have the control. What should I do? So
when you share your PowerPoint, you get muted?
Yes, so I think you have to unmute me, I guess. So
okay, well, I don't think I can, but are you joined on two different devices?
No, it's a single. I just unplugged the another screen,
okay.
so it's
okay.
We'll try again.
Try again. Let's see. Yeah. You have to unmute yourself. Yeah.
Unmute myself because it's grayed out for me.
So go back to your Zoom window. You are going to share the
No,
presentation from there.
yeah, my computer, this is ECC computer, so we don't have Zoom. So we have to join from browser. So that could be the problem. So maybe my supervisor is next. So can you go first? And in the meantime, I'll forward my presentation to one of the co-hosts, and then they can share for me.
Sure.
Yeah.
Okay,
That's
so
Frank.
we're going to go on to the next talk, which is Frank is going to talk about future water levels for the Great Lakes under 1.5 to 3 degree warmer climates. Are you ready to go, Frank? Okay. I've lost him. Oh, my goodness. Okay. Oh, you're muted. Well, you're not muted, but we can't hear you.
Now it looks like you're okay. Could you speak, Frank?
Yeah, now try it. I changed my speaker. Okay. So Narayan, what I was going to suggest is, just to keep us on time, I have your getting your presentation up. So I could show your presentation and you could do the audio part. Maybe that would work.
Yeah. Okay.
Okay, I'm just trying to find it. It keeps. Do you have the link in the? Can you put the link in the chat there, Narayan?
Yeah, sure. I'll do it quickly. Yeah.
Didn't work. Sorry about this, everyone. Oh, no, I have it, Narayan. Sorry.
Yeah. Yeah, I send you in the MS Team. Yeah.
So we're gonna go. Going to. Almost there. Sure. So are you seeing my screen?
Yeah.
Yes. So you can hear me, right?
Yeah, and we can hear you, Narayan.
Yeah. Sorry for the delay. I don't know what happened. So I'm Narayan Shrestha. Today I'm going to talk about land hydroclimatology of the Great Lake region in changing climate. So Frank is my supervisor who is helping me out with the slides. And I would like to thank other co-authors, Andre and Armin. So I'm located at Burlington. I work for Frank at Boundary Water Issues Unit of Environmental and Climate Change Canada. Next slide, please. Yeah, so the Great Lake region is one of North America's largest water resources system with an area of more than 766,000 kilometers square. And the freshwater resources of the Great Lake Basin is very important to almost 30 million people who live in the region, which is almost 10% of the population of the USA and 30% of the total population of Canada. Just to give you some figure to illustrate the importance of the freshwater resources of the Great Lake region, the fisheries in the region is valued at 7 billion. Similarly, recreational activities are estimated to generate another 16 billion US dollars. And of course, there have been a lot of studies, climate change studies of the region. But what we have seen is lacking in comprehensive assessment of the land area of the Great Lake region, specifically considering some of the auxiliary variables like snow water equivalent, evapotranspiration, and things like that. Next slide, please. So the modeling tool that we used for the impact assessment is a coupled model between wart flood and ravine. So using wart flood, we simulate the land surface processes. So that is also sometimes referred as vertical flux. So the vertical flux that have been calculated by the wart flood is routed through the river and lake using a recent routing product. Which considers all the smaller lakes or all the lakes which are more than 5 kilometers square in area. So this consideration is quite important for Great Lake Basin because one of the important characteristics of the basin is the presence of numerous small lakes. So this routing product has been incorporated in Rabin modeling framework. So we run Rabin in routing only mode, and then we couple wart flood and Rabin to make a coupled hydrological model to simulate the hydrological processes of the basin. So this couple model has been calibrated and validated against daily stream flow at 134 and 59 gauging station respectively, which are across the Great Lake domain. And the model is evaluated against daily snow water equivalent, actual evapotranspiration, and a top layer which is 10 centimeter soil moisture. I'm not going to talk about calibration, validation, evaluation of this couple model. We have a paper which is in discussion in the Hayes journal. So in that paper, I can share you the link of the paper. The paper deals about all the model development, calibration, validation, evaluation of this model along with other model, because the GRIP-GL project is about model intercomparison project in the Great Lake region. Next slide. So the future data that we use for this study is coming from the CMIP-5 NA Codex experiment. So the temperature resolution that we use is 0.44 degree, which turns out to be about 50 kilometer horizontally. The data has been bias corrected using multivariate quantile mapping bias correction technique of Canon. You can refer the paper from Canon in 2018. This is using 10 kilometer diameter data. We use 36 simulations from 6 regional climate models, and as with other studies, most of the studies, I would say, we considered 2 emission scenarios, RCP 4.5 and RCP 8.5. And for the assessment, we considered 2 future periods, mid-century period spanning from 2035 to 2064, and an in-century period spanning from 2065 to 2094. And all the comparison has been made with respect to a baseline period spanning from 1951 to 2005. Next slide. So here you can see sometimes there's plots of annual precipitation in the baseline period in your left panel, and in the future period in the right hand panel for both RCP 8.5 red lines and red shades, and for RCP 4.5 blue line and blue shades. What we can see here using Mankindle's test is at 5% significant level is the precipitation, the annual precipitation is already increasing with the rate of 8.6 millimeter per decade in the historical period, but that increasing trend is not present, at least for at 5% significance level for RCP 4.5 in both periods. But for RCP 8.5, there is still an increasing trend, even higher than what we observed in baseline period. In quantity, 10.2 and 13.7 millimeter per decade in mid-century period, and in century period of RCP 8.5. Next slide. So in terms of monthly, seasonal, and annual time scale, what we have seen is overall weather future condition. Frank, you have to click because I have some numbers in the slide. Yeah, so in the annual time scale, what we have seen is overall weather condition in the Great Lake land region. So with precipitation increases almost 15%. Can you click again, Frank? And even higher increases are observed for some month. For instance, for superior subdomain, we observed 39% increase in April precipitation, whereas in summer month we observe some drier conditions specifically for RCP 4.5. For instance, or in the Lake Erie subdomain, decrease of 6% is expected in century period of RCP 4.5 scenario. Next slide. The overall increase that we have seen in the previous slide will be in the form of intense rainfall or intense precipitation, I would say. Here, to support that argument, here we have precipitation days PD with precipitation accumulation more than 5 millimeter, 10 millimeter, and 20 millimeter. What we have observed is increases in the precipitation days with a specific amount of rainfall totals, especially for the higher rainfall 20 millimeter. The increments are almost double for RCP 8.5 and in the in-century period. Next slide. The same argument is also supported over here. For instance, what we have seen in the middle picture or middle bar plot is the number of wet days are almost constant or even decreasing in future, and also the consecutive wet days are decreasing definitely in future. However, the highest one-day precipitation, the leftmost panel, shows that the highest one-day precipitation will increase significantly in future. So that means we will have less number of wet days, less number of consecutive wet days, but overall increase in precipitation can only be happening if we have intense rainfall events in the future. Next slide. Similar time series plot for annual mean temperature. Again, we are talking about the Great Lake land area. So we have to be clear about that. In this presentation is only about land areas. So what we have seen in the left panel is historical, and in the right panel is in the future period. At 5% significant level, the mean temperature was already increasing at the rate of 0.2 degree per decade, which will almost be present for RCP 4.5 and in the mid-century period, the blue line. But there would be no increment, at least no significant increment in annual mean temperature in RCP 4.5 and in the in-century period, which is kind of expected because we have seen in previous presentations as well that the carbon sequence will be almost constant in the in-century period for the RCP 4.5. Whereas for RCP 8.5, for both periods, we have seen significant increases in annual mean temperature. The rate of increases are almost 3 times higher than what we have observed in the baseline period. Next slide. Frank, again, you have to keep clicking. So here, a similar plot in monthly time scale, seasonal time scale, and annual time scale. So what we have observed is significant increases in annual, mean temperature, not annual, but in different time scale. In the northern subdomain, the increases are higher than the southern subdomain. For instance, in superior, we have seen that the annual mean temperature increases would be on average 5.2 degrees centigrade, whereas the same for Erie would be 4.7. The increases in the monthly time scale, specifically in the winter month, would be even higher, 6.5 degrees centigrade higher than the baseline period. Next slide. So here, the same argument is supported with the less number of ice days in future as compared to the baseline period. So ice days are quantified as the days where the minimum temperature falls below 0 degrees centigrade. And in the right panel, we have the summer days, which is characterized by the days where the maximum temperature would be more than 25 degrees centigrade. So in future, the summer days would be increasing significantly, almost doubled, specifically for RCP 8.5 and in the in-century period. Now let's go to this auxiliary variable. First off, the snowpack or snow water equivalent. So what we have observed is although we see increases in the precipitation, but the increases in the mean temperature would be detrimental as far as the snowpack is concerned. So what we have seen in the annual time scale is some subdomains, for example, Erie would lose almost 3/4 of its snowpack in future in the annual time scale, whereas in monthly time scale, for example, the Ontario subdomain, it will lose almost all of its snowpack for the May of month. But the decreases in the northern subdomain of the Great Lake is not that severe. For instance, in the winter period, only 35% of the snow pack would be lost during the winter season. Next slide. So in accordance with the increases in mean temperature, we see the increases in actual evapotranspiration, specifically in the later summer and early summer months. But what we have also observed is during the autumn season, specifically the early autumn season or October, and in some subdomain, the decreases in actual evapotranspiration. So the potential evapotranspiration would follow the trend of mean temperature, but the actual evapotranspiration will also depend upon the amount of soil moisture. The depleted soil moisture because of increases in the previous months, evapotranspiration will have some effect in this decrement of actual evapotranspiration in early autumn months. Next slide.
No,
So
and
here,
just because we're running, I'm worried they're going to kick us out of the room. So if you can maybe wrap it up a little quick, so we have time for Frank to speak as well.
Sure. Next slide, Frank. I would try to go to the uncertainty now. Next. So here, what we have done is quantifying the relative contribution of emission scenario versus RCM uncertainty to the total uncertainty. So what we have seen for each variable, the contribution of emission scenario uncertainty to the total uncertainty is significantly higher. So that means that the choice of a particular RCM is not that important as the choice of emission scenario as far as the runoff, snow water equivalent, and AAT dynamics in the future of the Great Lake land region is concerned. So to conclude, next slide. So we have seen that the Great Lake land region will experience a wetter and warmer future, but even if it's wetter in overall terms, the summer will be drier. We have seen significant loss in the snowpack. Actually, evapotranspiration will increase, specifically in the summer month. The increases would be as high as 0.4 millimeter in a single day. Then we have also quantified that there would be consistent increases in the runoff component of the net supply to the lakes. And then uncertainty analysis so that the choice of a particular RCM is not as important as the emission scenario as far as the total contribution to the as far as the relative contribution to the total uncertainty to runoff, actually evapotranspiration on snow water equivalent is concerned. With that, I would like to conclude.
Great, thanks a lot. In the interest of time, I think I'll just ask people to put the questions in the chat and then maybe you can answer them directly. And we'll move on to our last presentation about future water levels of the Great Lakes under 1.5 to 3 degree warmer climates.
Okay, hopefully you guys can hear me.
Yeah.
Okay, cool. The rest of these talks have been more on the agricultural and forestry. Ryan and I are more straight water resources people, so hopefully you're enjoying this perspective. And kudos for anyone who's stuck around as it's getting close to 6:30 p.m. here on the eastern side of the country. So just going to give a quick background. Don't have to do as much because Narayan did a lot of the background, talk about what's called net basin supply, and then get into the projection of the future lake levels and some take-home messages. So the background is using Cordex runs, just like Narayan did. Not that surprising. So the important thing is they have a resolution of about 25 kilometers. Why do we have to use these? It's because of this. When you look at the GCMs, the resolution of the GCMs in the bottom left here, you'll see that the GCMs have their resolution is about 150, 200 kilometers in the Great Lakes. Therefore, we have to downscale because also, as Narayan showed, just when you look at the watershed area of, let's say, Lake Superior, like almost 2/3 of it is the actual lake itself. So you really have to get the lake processes correct if you're going to get anything about the basin correct. So that's why we need to do these downscale. That's why we can't use all, I don't know, what is there, like 100 different, all the different GCM combinations. We're kind of limited to these specific ones here on the left. You can see the OCM GCM combinations we were able to use, and I'll explain why we couldn't use even all the Cordex runs later on. I won't even talk about 4.5 and 8.5. Everybody knows that. I just want to acknowledge that we, just like Narayan, we do have a bias adjustment. Not going to talk about it. It's based on the same Alex Cannon paper, who is not here, but he's been at this conference. I've seen his name around, but maybe he'll see this in the recording and know that I gave him a shout out. And then the thing that we do in our office is we can take the climate data and we can relate it to water levels. That's kind of a unique thing that we are able to do just because of our experience with the basin and the Great Lakes. So we take the Cordex runs, we make what's called RCMs. From the RCMs, we make what's called net basin supply, which I'm going to explain next, run it through a model, and then that gives us the water level projections. And that is, again, pretty unique. So talking about net basin supply, it's just a measure of the local water supplies that are coming into the lake. So the component net basin supply is the sum of the lake precipitation and runoff minus the lake evaporation. And of course, that is important because the precipitation and the evaporation are, fighting on different ends of as far as lake levels go. So we need values for the entire lake, and our reference data set is from the Great Lakes Environmental Research Laboratory, a NOAA shop in Ann Arbor, Michigan, which goes back to 1950. So we can look at things like kind of similar-ish to what Narayan was showing. You see we have the observed lake precipitation. This is just precipitation over the lake. That's what we need for NBS. And then on the right-hand side, we have future projections. We've just decided to do it with a bunch of spaghetti plots, so you can see all the different plots. You can see the blue is the 4.5, red is the 8.5, and you can see the different trends. The most important thing is, just like Narayan found, there's an increasing trend in precipitation in the basin. And then next you have the runoff, also an increasing trend, but also important now, lake evaporation also has an increasing trend. And as I said, this is kind of offsetting that increasing trend in precipitation. So it's not a slam dunk to say, oh, well, there's more precipitation, the lake levels are going to go up. No, because the lake evaporation is also increasing. So it's really going to be the change in the rates of the evaporation and the precipitation that's going to dictate the future water levels. And that's where it gets a little bit complicated. And we put all those together and we get this net basin supply, where you'll see that it's got this very slight kind of rise in it, but much more muted rise than we saw in either precipitation and evaporation, again, because they're offsetting. So they're canceling each other out. But there is a slight rise, especially near the end of the century. So now we get into the future lake levels. We have to run this through what's called the Coordinated Great Lakes Regulation Routing Model for the Upper Lakes, and a separate model for Lake Ontario. We split the Great Lakes into the Upper Lakes, which is everything upstream of Niagara Falls. As you can imagine, Niagara Falls is a bit of a break hydrologically as far as the two different sides of the basin. One side doesn't really influence the other. So we have to have a separate Lake Ontario model. And this is also because what this model does, we've got the lake levels, but it's about the connecting channel flows between the different lakes that are important, because some of them are unregulated and some of them, like the outflow from Lake Superior and Lake Ontario, are regulated. So you have to have the regulation plan in your model as well if you're going to properly simulate what's happening on the Great Lakes. And then this is an important thing, is that some of the assumptions that this model was designed for regular conditions. Now, when we start talking about climate change, especially some of those extreme runs of precipitation, well, you're going to see some things that the model really wasn't designed for. So maybe some of the assumptions are going to start to be violated. And these are things we're going to have to look at in the future. For example, there's no maximum flow in the connecting channel. So for instance, the Detroit River can just have as much flow as Lake Huron will pump out, which, you know, eventually it's going to go onto the floodplain. It's going to slow it down. It's going to have a different regime, but the model isn't sophisticated enough to figure that out. Now, instead of presenting the lake levels like this, which is more the classic way of having the measured lake levels on the left, and then we project them out to the future. When going out to the public, RCP 4.5, RCP 8.5, you know, general public has not heard of that. But what they have heard of, you know, if they're kind of paying attention, is the change in global mean temperature. A lot in the news about, you know, keeping the change less than 2 degrees, less than 1.5 degrees, Paris Climate Change Accord, you hear all that. So Raj, who also has been on this conference, but I don't see his name here, led me to this. So this is basically, you look on the left, you can see the different RCMs and the different scenario you're looking at. You can actually pick out, okay, this is the 30-year period where the global mean temperature changes by 1.5 degrees, where it changes by 2 degrees, and so on. So you can actually split it up that way. So then hopefully this comes out well enough on your screens. You can see here, so what we've done is taken Lake Superior on the left, the classic, we got them measured for the last 1918 to 2020, but then each one of the kind of 4 sections of the spaghetti plot are, okay, here are the projected lake levels if the change in global mean temperature is 1.5 degrees, 2, 2.5, and 3 degrees, and in a nice 30-year sequence. And it's not so obvious on Lake Superior, so I'll do it where it's more obvious on Lake Huron. So what you can see on Lake Huron is that even under 1.5, the highs and the lows, we see more of these extremes. And then as you go up higher and higher in global mean temperature, you see even more and more of these extremes, which I think is just a really good way to say, hey, you know, this is why it's important to keep that, you know, change in global mean temperature less than 2 degrees, less than 1.5 degrees, because we'll see less of these extremes. And of course, Lake Erie, we see that expanding range as well. And Lake Ontario, because it's regulated, you can see the effect of the regulation, that most of the spaghetti plots are kind of within that narrow range, because that's what the regulation is trying to do, of course. So it's just in these very extreme instances, and you see them even more as you get into the higher changes in global mean temperature. Even the regulation plan can't handle all the water that's coming in. So Lake Ontario is going to look a little bit different. Now we can just imagine we summarize all these instead of these spaghetti plots. What I've done here is actually just taken those spaghetti plots and made just nice box and whisker diagrams. So a little bit easier to see, but you can look at Lake Michigan Huron. You can see that compared to the measured range, which we've seen, like we all know what box and whisker plots look like, you can see how the range increases as you go more higher and higher in change of global mean temperature. And the same thing for the other lakes, depending on your extent. And we put a line down there for the zero changes in the, and this is lake level difference from the reference period. So you can see that the median in general kind of increases in the box and whisker plots. But I think you can also see that it also maybe isn't as significant as those change in extremes. So we always say in the Great Lakes, it's not the average water level that's going to flood your road or take out a building. It's those extremes. So you can really see that it's the changes in the extremes that's more important than the change in the average over these different changes in global mean temperature. So just going to throw out a couple of take-home messages. First of all, changes in the there's more extreme lake levels, both highs and lows, and you'll notice there are also some projected lows in there under a changing climate. I'd actually be interested if people want to put in the comments here, is this a good way to show it? Like, are people, do you think this is more for the public or even more for scientists, an easier way to digest what the changes are going to be, as opposed to saying a certain time period with RCP 8.5, 4.5, just to put it this way? I'm very interested in people's opinion. Kind of came up with this. We kind of like how these graphics look. But anyway, it's the changes in extreme that are the most important thing. Probably people here realize it, but it's important to say it to the public, is that it's not a certainty, even though we show in some of these models have a very high extreme lake level, you know, we don't want people to panic and say that 100% that is going to happen. So tried to put it here. It's like that lottery, like a lottery, you know, big ball thing where they put the little balls inside the big turning spinning globe. And so you say that the red on the left side, you've got the green, which are the nice normal water levels, and the red is the more extreme water level. Well, in the current climate, you've only got one ball that's coming out there, so it's got a certain time, certain chance to get picked. And then as you go from 1.5 to 3, well, now you're putting more of those extreme balls into the big globe. But it doesn't necessarily mean, even in the 2.5, you could still go through a 50-year period and never actually, you know, have one of those red balls, never have one of those extreme water events. But it's, of course, the odds are greater. So that's what we're trying to say there. It's not a certainty, but it's certainly increasing the possibility. And the third one is that what's actually going to happen? It all depends on society. Are we going to keep to the 2 degrees? Like you see the headlines there, 2 degrees or 1.5 degrees, 1.5 goal on life support. So, you know, how humans react to the climate crisis and what actual changes are made. That's really going to be what's going to happen. So I can't predict it. Nobody here can predict it. But what we can say is that based on what we've seen, if we have certain amounts of changes of the global mean temperature, we can see what the consequences are going to be and maybe get some reasons of why we should keep it below 1.5 or 2 degrees. Got a journal article. It's being accepted in the August edition of the Journal of Great Lakes Research. And I'm going to end it there.
Thanks, Frank. Thanks for doing that quickly. Well, they haven't kicked us out of the room yet. So if anybody has a question for either of our last 2 speakers, go ahead. I actually have a question. Does your model, you talked about the regulation on Lake Ontario, presumably those extreme event years, the water has to go somewhere. Where's the water going? Is it going into one of the other lakes or is it going somewhere else in the basin?
Sorry, I'm moving my screens around here. Sorry, so when you say the extra water, what do you mean by that? Sorry.
Oh, when you're showing these high lake levels, but the Lake Ontario levels are not fluctuating in as much, but presumably the amount of water is still
the amount of water. There'd be more outflow during those times, and then in times when it would have been lower, keeping back some of the water to keep that water level back into the average. So obviously didn't show the outflow, but it's all about the controlled outflow. That's what's influencing the lake levels. So that's where it's going, further downstream. And I can't see the chat, so
yeah, we have a question in the chat. Great talk, Frank. Do you plan to apply some statistical analysis to better or show changes in extremes? Example, GEV.
That's certainly, we were just trying to get this out. We had another project where we had to produce these water levels. So now we can take a little bit of a breath and Bilyani, we can do some of these more detailed looking at these extremes and doing more statistical analysis. But I'd be glad to talk to you about it anytime.
Great, thanks a lot. Okay, well, I think we'll wrap it up there. Thanks everybody for hanging around for the session. I think there's some really great talks here and I definitely learned a lot. I think this is the last of our ag forest meteorology sessions, but I hope you enjoy the rest of the sessions on next week. So take a look at your schedule and plan to attend some more CMOS sessions next week. All right, and have a good weekend, everybody.
Have a good weekend.
Thank you.